Section 1.5 Factoring. As I mentioned in the last section, out of all the sections in this chapter, in the first chapter, factoring is by far the most important section. So please make sure that you understand the concepts of factoring really well, and not just understand them, but are able to apply them very fluidly. Okay, so let's get started. Let's first talk about what we mean by factoring. Whenever I ask students what factoring is, they give me all kinds of definitions that they've come across. But to me, factoring basically means is you want to write something as a product. You want to write as a product. And that is the most important thing about factoring. And in the process, things tend to get smaller than what you start with. So here are some examples with just some numbers. So like for example, if I want to factor 15, I want to write 15 as a product. So I can write it as what? 3 times 5. So we wrote it as a product. If you have a number like, for example, if I have 12, 12 can be written as 4 times 3, but then that can be factored further since 4 can be written as a product too, so we can write it as 2 times 2 times 3. So these are some examples of factoring. The key takeaway is always remember, when we talk about factoring, we want to write something as a product. And students always tell me factoring is when you write something using smaller numbers. But that's true. But like out here we wrote 15 as 3 times 5. But the key thing is we are writing it as a product. That's the most important idea to take away. So what we want to do in this section is we want to factor polynomials. That's what we want to do. We want to take a polynomial and write it as a product of other polynomials. Okay, that's what we want to do. So let's go ahead and get started with that idea. Factoring polynomials. Anytime you're factoring polynomials, you need to go through some basic steps in your head always, and I'll give you these steps. Okay, these are very, 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 very important steps, so please remember that. The first thing you do anytime that you want to factor a polynomial, you look for something called the greatest common factor. Okay, and you do these steps in order, and greatest common factor. And once you do one step doesn't mean you're done, you apply the next step. The second thing you do when you're factoring is you look at the number of terms in your polynomial. Okay, you look how many terms your polynomial has. We talked about the number of terms in one of the previous sections, in the last section. Now, if the polynomial has 2 terms, then we're going to use a formula. And we'll talk about that, all the different formulas you need to know. On the other hand, if a polynomial has 3 terms, then we're going to use the AC method. And I do want to mention this, we're talking about 3 terms, and we're also talking about degree 2. Okay, and we'll talk more about each one. And then the last thing is, if the polynomial has 4 terms, we use the method of grouping. So these are the steps you're going to perform anytime you're doing factoring. Okay, so please remember these steps. They're going to be very useful to you in the long run. So let's get started by looking at the greatest common factor. Okay, I'll just abbreviate that, greatest common factor. So basically what we're trying to do is we're trying to find a number, a algebraic expression. Let me rewrite that. For the greatest common factor, we are trying to find a quantity in the polynomial that is common to all the terms of the polynomial. So I do want to kind of clarify things. Now the quantity could be just a mathematical quantity, like it could be variables and numbers and so on. And when I say common, I really mean it is a factor of. Okay, and I'll show you by example what I mean. When we're doing greatest common factor, we're really, the idea here is to do the distributive property that we learned in basic math in the opposite direction. So like here's the idea. This is similar. Let me just do the distributive property. So that is, for example, we've always learned that if you're given a times b plus c, what do? We distribute, right? We distribute this a, so we get ab plus ac. That's what we've been programmed to do from in basic algebra. What we want to do is we want to do the opposite. That means we want to go in this direction instead of going in this direction. So let's say if we're given this AB plus AC. Now I have two terms here. What's common in both those terms? What do both those terms have? Because it's written as a product, these already factored, just so you guys know. But what's common in both of these terms? Both of these terms have the quantity of A. So I can take that A out. Okay. Now what do I take out of the two terms? In essence, you're dividing each of these terms by that. So if I divide this by A, the A's cancel, so I'm just left with B. And if I divide this by A, the A's cancel, so I'm left with just C. So that's what we are trying to do in this section. Given a polynomial, we are trying to write it as a product. So we factored out the A. This was the largest thing that was common to both of these terms. Okay, so that is the idea of greatest common factor. We're trying to find a quantity in the polynomial that is common to all the terms, that all the terms have that quantity in it, so we can take that quantity out of every single term and write it in the front and then write it as a product. If we were to distribute this, we would get this back. So you can always check your answer when you do factoring. That's a nice thing about factoring. So let's go ahead and take a look at some examples and see how this is going to help us factor polynomials. Let's start with something simple. So let's say if you have 2x squared minus 12x. Okay, if you look at this polynomial, I want to factor this. They've asked us to factor. That means they want us to write it as a product. Okay, so let's take a look at the numbers first. I have a 2 here and a 12 here. Now in your head, you just have to go through numbers and find a number, the biggest number, not just a number, but the biggest number that can divide 2 and also divide 12. In this case, the biggest number that can divide both of them is 2. Okay. Then let's take a look at the variables. How many x's do I have here? Because it's x squared, I technically have x times x, so I have 2 x's. And out here we have just x. So the greatest number of x's that are common to both these terms is just 1, because they both have 1x. So I can take that x out. So now I took those things out of those two terms. So what's left now once I take those things out? Well, I took the 2 out, so the 2 is gone. I took one of these x's out, so that's gone. So I'm only left with 1x minus. Over here, I took the 2 out. Remember what I said earlier. Whatever you take out, you're dividing by that in essence. So what is 12 divided by 2? I get 6. X divided by x is just 1, so that's all we get. Okay, so the key thing is we wrote this as a product. That's what we wanted to do. Okay. Now, another way to look at this is, like I said, it's factor. So let me show you why I wrote it that way. Let's do the same example so you can see the definition apply better. I have 2x squared minus 12x. So let's factor this number. 2 cannot be broken down any further, so it's just 2. X can be broken down into x times x squared, I'm sorry. Minus 12 can be broken down into 2 times 3 times x. We've talked about that. So we're already factoring each of these things individually. Now we look for the greatest common factor. What's the biggest factor that's common to both of them? There's a 2 here, there's a 2 here, so let's take that out. So that's gone. There's an x here, there's an x here, so let's take that out. So that's gone. Okay, So now what's left then? There's an x left minus, I have 2 times 3 left, which is 6. So that's really what's happening under the hood over here. We don't do these detailed steps because they're too tedious, especially if the numbers get really big and I have power 8. You're not going to keep writing x 8 times, but you can get the idea of what's going on. We are basically trying to find a quantity that's common to both the terms, and once we find that quantity, we take that quantity out and we divide each of those terms by what we took out. Because if we were to multiply by 2x here, we should get this back. And that's a nice thing about factoring. Like I mentioned a minute ago, you can always distribute again and see if you can get the same value back. And so we know factoring was correct. Let's take a look at some more examples of the greatest common factor. So let's say if I have 6a cubed b squared minus 12a squared b plus 15ab cubed, and they want me to factor this. Anytime they want you to factor something, remember those steps I just gave you? You need to go through those steps in your head mentally every single time. These steps, these should be, like I said, very important to you. You just need to perform these steps every single time in that order. Okay, so let's start with the greatest common factor first. Let's look at the numbers. Always start with the numbers. What's the biggest number that you can think of that divides 6, 12, and 15? Okay, and the number in this case is 3, because 3 divides 6, 3 divides 12, and 3 divides 15. Then you look at the variables. How many a's do I have here? A cubed, that means technically I have a times a times a, 3 of them. Out here I have 2. Out here I have 1. So what is the greatest number of a's that are common to each of those terms? Well, there's only 1 here, there's 1 here, and 1. So I can only take out 1a. So let's do that. That's the greatest number of a's that are common to all 3 terms. Similarly, this time I'm not going to break them down, just do it in your head. I have 2 b's here, 1 and 3 here. So the greatest number of b's that are common to all of them is just 1. Okay, because I can't take 2 of them out because this would be short because I only have 1 here. So let's see what's left. Okay, whatever I take out, you divide each term by that. So if I divide this by this, the 6 divided by 3 is 2. A to the 3 divided by a is a squared. B squared divided by b is just b. Minus 12 divided by 3 is 4. A squared divided by a is a. B divided by b is just 1, so we don't need to write that. 15 divided by 3 is 5. A divided by a is 1. B cubed divided by b is b squared. And there's your answer. Okay, we wrote this as a product. That was a key thing. Now sometimes things might get a little interesting, so let's take a look at that. Let me just do 2 last examples of this. Let's say that I have minus 5x cubed plus 10x squared. Okay, now let's factor this again. They've asked us to factor. Anytime they ask us to factor, we look for the greatest common factor, thing that's common in all the terms. So let's start with the numbers. There's a 5 here, there's a 10 here. Can you think of any number that divides both of them? Sure, the number is 5, so I can take out a 5. Okay, now I have 3 x's here. X cubed is x times x times x, and I have 2 of them here, so the greatest number of x's that are common to both of them is 2. Okay, so I took those 2 things out. Now this is just my preference, and I've noticed that it is a very good thing to do whenever you're factoring polynomial. We first of all always write polynomials in the decreasing order of their powers. You've seen me do that. I haven't mentioned it before, but I'm hoping you pick that up. And the other thing to note also about polynomial is never have the leading coefficient be negative. That's something that really helps you out later in this class. That'll help you out later in this class. So it's always a good idea, if this is negative, instead of dividing by just 5, let's divide by minus 5. Okay, so what is negative 5 divided by negative 5? Just 1. X cubed divided by x squared is just x, because I can get rid of 2. Positive 10 divided by negative 5 is negative 2. X squared divided by x squared is just 1, so we just get this. Okay, I really want you to get into the good habits. If the leading coefficient of a polynomial, leading coefficient, that means the first term of the polynomial is negative, always take that negative out. It'll really help you out. Okay, here's another example that illustrates something a little bit different. So let's take a look at that. Let's say if I have minus 4x cubed plus 2x. Okay, they've asked us to factor. So let's do that. Look for the greatest common factor first. So let's look at the numbers. There's a 4 here and a 2. What's the biggest number that divides both of them? That's 2. Okay. I have 3 x's here, 1 here. So the greatest number of x's I have common in both those terms is just 1. They both have at least 1 x in common. Now, the leading coefficient is negative, so let's fix that. So let's take out a negative 2. Always take out that negative sign. So what am I left with? Negative 4 divided by negative 2 is just 2. X cubed divided by x is x squared. Positive 2 divided by negative 2 is negative 1. Okay, and x divided by x is just 1. So there's your answer. Because out here there was a 2x here, we took all of that out, so I'm just left with a 1. Okay, so don't forget that students sometimes have a tendency to write this way because they feel like they took all of this out, so it's no longer there, so it's 0, so they don't write it. But if I were to distribute it, I'll just get what? 4x cubed. But then I would miss this term, because remember, the nice thing about factoring is once we factor, we can always distribute to see if we get this original polynomial back. And in this case I don't. I just get the first term of the original polynomial back. I don't get that second term. Okay, so that's factoring using the greatest common factor. Okay, the next thing we want to do is we want to talk about factoring two-term polynomials. And we already agreed that we're going to use a formula for that. Anytime you have two terms, we always want to use a formula. So let's quickly learn some formulas. In the last lecture I gave you 3 formulas. In this lecture I'm going to give you 3 more, and that's all you need to learn is 6 formulas. Okay, so let's start with the first one, which is pretty much the same as the first formula I gave you last time, which is this: if you have a squared minus b squared. If you have a squared minus b squared, I can write them as a product of conjugates. I get a minus b and a plus b. If you remember that, these were conjugates. In the previous chapter section, we were doing the opposite. We were given 2 polynomials and we were multiplying that to get this. This time we want to go the other way because we want to write it as a product. We want to actually write this polynomial as a product. So we want to go in the other direction. This formula, like I told you before, has a name. It's called difference of 2 squares. And you can see that from the left hand side. I have a difference of 2 squares. Okay, so that's one formula. The second formula is a cubed minus b cubed, difference of 2 cubes. We get a minus b, we get a squared plus ab plus b squared. And there's really no other way to factor this polynomial unless we know this formula. So it's very important that you guys know these formulas. This is difference of 2 cubes. And then the last formula you need to learn is a cubed plus b cubed, which is a plus b times a squared minus ab plus b squared. So this is sum of 2 cubes. So these are the 3 formulas you need for this class. And you can see on the left hand side I have some polynomial because it's a polynomial. Why? Because the exponents are positive integers or 0. And on the right hand side we've written the left hand side as a product. And that's our goal. Okay. Now, before I show you how to use these formulas, let me mention 2 things. Note 1, there is no formula for sum of 2 squares. There's a formula for difference of two squares, but there's no formula for sum of two squares. The second thing you need to note is always write the polynomial in the left hand side form of the formula before using the formula. And I'll explain that when I do an example. This is important because sometimes students get confused what they're doing with those formulas, but if you perform this step, it'll really make life easy. So let's take a look at some examples. So all of these examples are going to ask us to factor. We've talked, that means writing it as a product. So let's start with the first one. Okay, let's say something really simple. Let's say if you have x squared minus 36. Now, the first thing, whenever they ask us to factor, the first thing we always do, don't forget, is look for the greatest common factor. So let's see. I have a 1 here, I have a 1 here, and a 36. So in terms of numbers, there's no number that divides 1 and 36 other than 1. So that's a trivial number, so we don't need to worry about that. There's an x here. I have two x's here. I have no x's here, so I can't take any x's out either. So I cannot do anything with the greatest common factor. So that's fine. The next thing we do is what? When we factor. Once we take care of this, we look at the number of terms. How many terms do I have here? Well, I have 1 and 2. So I have 2 terms, so I need to use a formula. And the nice thing is, anytime you have 2 terms, you're down to these 3 things. If you cannot use one of these formulas, then you're done, because you cannot break that polynomial down anymore. You can't factor that. So let's take a look at how to do this. To use this formula, to factor this, we need to use one of these formulas. And since I have a square here, and I know 36 can be written as what? 6 squared. That tells me I want to use difference of two squares formula. So the first thing, what did I put in this note? First, always write the polynomial in the left hand side form of the formula. So first thing I want to do is write it this way. Actually write it as difference of two squares. So let's do that. X is already written as a square, and then I'll write 36 as 6 squared. Now that I've done that, let's factor this. According to the formula, anytime you have difference of two squares, you can write them as a product difference of their conjugate. Write them as a minus b and a plus b. Write them as product of two conjugates. So in this case, we get x minus 6 and x plus 6. Okay, so this is my a, this is my b. Remember, a and b are the terms without the squares. Okay, they are the base. A is x, x is my base here of this number, a is that, and b is the base of this number, which is 6. So you get a minus b, you get a plus b, you get the product of the conjugates. You guys remember that, right? Alright, so that was an easy problem, but the key step is this step here, to write this way. Once you get good at this, like I said, once you master something, then you can start skipping steps, but till you master things, try to be concise and try to be precise. Okay, not concise but precise as with your work. So let's go ahead and take a look at the next example. Let's say if I have 4x squared minus 100. Again, they want me to factor this, so look for the greatest common factor. I have a 4 here and a 100. Can we think of a number that divides both 4 and 100? Sure, it's 4 itself. Okay, I have two x's here, I have no x's here, so I can't take any x's out. So let's just write down what's left. 4 divided by 4 is 1, so I'm just left with x squared, minus 100 divided by 4 is 25. Okay, the next thing I want to do is, I'm not done. Just because you did the greatest common factor doesn't mean you should stop. You have to continue. You look at the number of terms. I have 2 terms, so I want to use one of those formulas. Those formulas both involve a square. We have difference of two squares or cube, difference of two cubes or sum of two cubes. So ask yourself, can I write both of these numbers as either squares or cubes? If I can, then I can use one of those formulas. So let's see. I have 4. X is already written as a square, but then I can write 25 as 5 squared. So that's good. So I was able to write both of them as squares, so I want to use difference of two squares. In this case, my a is x and my b is 5, because a and b are the base of these exponential numbers. So according to that formula, I get what? A minus b. So I get x minus 5, and then I get a plus b. I get x plus 5. I get the conjugates, basically. We've talked about that. There's your product. Okay, that was another nice easy problem. Let's take a look, keep moving and take a look at some more harder problems. How about this one then? Let's say if I have 16 x to the 4th minus 1. Okay, and I want to factor this. I have a 16 here and a 1 here, so they have nothing in common, okay, other than a 1, which is a trivial value. I have x's here, I have no x's here, so I can't take x's out, so there's no greatest common factor. Then I have to look at the number of terms. I have 2 terms, so I know I have to use one of those formulas, but all of the formulas that I have involve either the square or the cube. You can clearly see this is the 4th power, so this is not a square nor a cube, so can I even use these formulas? You can, so don't give up on things too easily. Always ask yourself, can I do some math manipulation to make me so that I can use one of those formulas, because that's the only choice I have when I have 2 terms. Well, let's be a little bit creative. Now, this x to the 4th and the 16 can be written as a square. It cannot be written as a cube, but it can be written as a square. So that tells me that I might have to use this formula. So let's try. 16 is what? 4 squared. How about this number, x to the 4th? Can I write that as a square? Sure, I can. Remember, there was a property of exponential numbers. I can do this x squared squared, because 2 times 2 is 4, right? So I can do that. So I can definitely write that as a square. So let me go ahead and write this a little bit neater. So I can write this as 4x squared squared, because 4 squared is 16, x squared squared is x to the 4th, minus, and 1 can always be written as a square, because 1 squared is 1. 1 times 1 is 1. So you can see I was able to write it as difference of 2 squares. Now here my base is this number. Out here my base is this. So my a over here is 4x squared, and my b is just 1. So what does the formula tell me? You take the product of the conjugate, so you get a minus b, so you get 4x squared minus 1, and then you get 4x squared plus 1. Now, you might be happy that you were able to factor this, but you have to take a minute and think about it too. Let's go back here originally when we started to point out something. Now, over here, if I were to factor 12, I get 4 times 3, and you might be happy with it. But remember, the whole idea of factoring is you want to write something as a product. Once you write it as a product initially, and you see that you can write one of those numbers again as a product, then you want to keep doing that. So then I get 2 times 2 times 3. So these are the factors of 12. So that's what we want to do with this example too. Even though we factored this to this, we wrote it as a product, I can actually factor these again. I can break them down into smaller products. So let's do that. Let's start with this one. Okay, this has 2 terms, nothing in common, so I don't have to worry about the greatest common factor. It has a square, and 4 can be written as a square, so I know I can write it this way: 2x squared minus 1 squared. So I can do that. Okay, so I'm going to come back to that. Remember, I'm just trying to write it in the left hand side form of the formula. Okay, how about this one? Can I use the formula for that? I can't, because there's a plus sign. There's no formula for sum of 2 squares. So this one stays the same. It doesn't change. But this one on the left here, I was able to break it down because that's difference of 2 squares. Now my a is 2x and my b is 1. So you get a minus b, so you get 2x minus 1, and you get a plus b, so you get 2x plus 1. Okay, and then we have 4x squared plus 1. So there's your answer. Now we cannot factor that any further, so we are done. So we wrote this as a product. So please don't get complacent and say, oh, I solved it, I factored it once, I'm done. No, sometimes you can factor things again and again. So you want to continue to factor till you no longer can. And always make sure that you write, when you're doing these factoring problems, you first write the polynomial as the left hand side of the formula, like write it this way before you apply the formula. It really helps to identify what a and b are. So we looked at a couple examples over there. Let me give you one last example that's a little bit more complicated. So let's say if I have this, I have 2x minus 3 squared minus 4. Now on the surface it looks like this is not a difference of two squares formula. First of all, technically this is one term, even though it looks complicated because it's got a whole bunch of stuff happening on the inside. It's one term. That's my base, that's my power. So that's one term. This is another term. Okay, so now there's nothing in common in these two terms. Okay, so I look at the number of terms. I have two terms, so I need to use a formula. I can only use a formula as if I can write this as difference of two squares, or sum of two squares, or difference of two cubes. Since I have a 4, that gives me a hint, because 4 can be written as a square, so that tells me I want to use the difference of two squares if I can. Now this term 2x minus 3 squared, that's already written as a square, so I'm done with that. But 4 can be written as what? 2 squared. So I wrote this as difference of two squares. You can see that clearly. Out here my a is something complicated. It's 2x minus 3, and my b is just 2. A is your base here, b is your base here. So what do I get? I get the product of the conjugate. So I get a minus b. So I get 2x minus 3 minus 2. And then I get a plus b, 2x minus 3 plus 2. This can be cleaned up a little bit. I can add these guys up. So I get 2x minus 5. And I can add these guys up. So I get 2x minus 1. So these are your factors. So sometimes problems might get a little bit interesting, but if you follow the same guidelines, you shouldn't have any difficulties with them. Okay, so we looked at some examples here of difference of two squares, a lot of different variety here. I showed you how we can be creative if they're not in terms of already a square or a cube, so to write that. How about this one? We didn't take a look at any cubes, so let's take a look at that. Let's say if I have x cubed minus 27. Okay, there's nothing in common. There's a 1 here, there's no x here, so I can't take out, there's no greatest common factor, so I can't take out any factors. The next thing is I look at the number of terms. I have two terms, so I want to use a formula. Well, usually the numbers will give you a hint what formula you can use, because I know 27 can be written as 3 cubed. That tells me that I want to use difference of two cubes, because that's where the cube is. So the numbers are usually the giveaway. They'll tell you what formulas you can use. Sometimes you'll have to be a little bit more creative, but usually numbers will guide you. So to use the formula, first I need to write it as difference of two cubes. X is already written as a cube, and then 27 can be written as 3 cubed. So now I have difference of two cubes. My a is x here, and my b is 3. A and b are always the base of those exponential numbers. According to the formula, I get a minus b. Okay, so we get a minus b, so we get x minus 3 times a squared. What is x squared? It's just x squared. Plus a times b, so you just multiply these, so you get 3x. Plus b squared. 3 squared is 9, and there's your answer. Okay, so that's a example of difference of two cubes. One last and final example. Let's say if I give you something like this. If I said if you have 8x cubed plus we have y to the 6. Okay, so nothing in common. You can clearly see that there's x's here, there's no x's here, there's y here, there's no y here, there's a number here, there's no number here. So there's no greatest common factor. You look at the number of terms. I have two terms, so I need to use one of those formulas. I only have choices of a square, difference of two squares, or difference of two cubes, a sum of two cubes. Which one should I use? Well, look at the number 8. 8 can be written as 2 cubes, so that tells me I need to write it as sum of 2 cubes. So let's start doing that. So this term can be written as 2x the whole cube, because 2 cubed is 8, x cubed is just x cubed, plus, how do I write y to the 6 as a cube? Because that's what I want to do. So let's see. I have y to the 6. Using properties of exponents, I can write this as what? Y squared cubed, because 2 times 3 is 6. So that tells me I can write y to the 6 as a cube. I can write it as y squared cubed. Now that I've written it as sum of two cubes, I can apply the formula. So let's identify a. A is the base of my first number, which is 2x. That's my base. B is the base of the second number, which is y squared, because that's my base here. So according to the formula, you have to memorize those formulas. So the formula tells me what? I gave you those earlier. You get a plus b, so we get 2x plus y squared. Then I get a squared. So what is 2x times 2x? We get 4x squared minus a times b. So you multiply these two. So we get 2x y squared plus b squared. What is y squared? If you square y squared, we get y to the 4. So we get y to the 4. So there's the answer to that problem. So I'm hoping that after doing some of these examples with formulas, I've convinced you how vital it is to memorize these formulas, because without the formulas, you cannot do any of these things. The nice thing is, anytime you have two-term polynomial, you know you have to use a formula. So that limits you in terms of what you can do. Okay. One last example, since I have some room here. If I had given you this, let's say we have 81x squared plus 49. There's nothing in common in either of these terms, so I need to look at the number of terms. I have two terms, so I need to use my formula. Now, to use a formula, first thing I have to do is see if I can write them as a square, because the 49 tells me is a square and 81 is 9 squared, so that's how I know I want to write it as a square. So I can write that as 9x squared plus 7 squared. But at this stage, you should stop yourself and go, wait a minute, that makes no sense, because I don't have a formula for sum of two squares, do I? So even though I can write each of these things as a square, it doesn't help me, because there's no formula for sum of two squares. There's only a formula for difference of two squares. So this polynomial cannot be factored. This is the best you can do with it. That's all. Okay. So make sure you don't apply formulas in situations where you don't need to. Okay. So that was the idea of factoring two-term polynomial. The next thing we want to do is factor three-term polynomials. So let's talk about that. This is E. So factoring three-term polynomials of the form ax squared plus bx plus c. So they have to have an x squared term, okay, and they have to have three terms. And to do this, we're going to use something called the AC method. There's many different ways to do this. Okay, there's three ways to do this problem, but I prefer the AC method. It might be a little bit longer for some of you, since you guys have already learned some methods from high school, but I really like the systematic nature of the AC method. Okay. So we're trying to factor a three-term polynomial of this form, so it has to be degree 2. Okay, so just so you guys know, it's a degree 2 problem. So let's talk about how we do that. So we have, this is the whole idea here. We have ax squared plus bx plus c. The whole idea is what? I want to factor this. I want to write it as a product. Correct? Since I'm starting with degree 2, I'm going to end up with degree 1 eventually, 2 degree 1 polynomials. That makes sense, right? So first thing I'm going to do is whatever number here is there, I'm going to put that here, here, and on the bottom. Okay, so just bear with me. If you've already learned how to factor this, you might find this really strange, but if you just follow along, it'll work out. The next thing I want to do is I want to go ahead and put the variable next to that. So I have x and x. Okay, so that's something you automatically do. So now the only other thing left to do is put these two numbers here, m and n. So you must be wondering, where am I pulling those numbers out? I know where a is coming from, that's here, but where are m and n coming from? So let me describe those. Where the product of m times n is a product of a times c. That's why the name AC method, a and c. And the sum of m and n is equal to the middle term. So this is pretty much the AC method. I like this method because it is very systematic. There's no trial and error guessing or anything like that with a lot of the other methods. Okay, so let's take a look at how to use this method. I will show you how to find these m and n's, but it'll be better if you can do them in your head like a puzzle. It makes it a lot easier. Eventually you want to be able to do that. Okay, just one other thing before I move on. Note, when using the AC method, the a term, this term a in the bottom, the a term in the denominator should always cancel. And I'll show you what I mean by that. That should always happen. There shouldn't be an a left in the denominator, even though we start with 1 in the denominator. So let's take a look at some problems that use the AC method. Okay, let me start with something simple. So let's say that if I have b squared minus plus 12b minus 28. Okay, so first thing we do is look for the greatest common factor. There is nothing in common. There's no number. There's a 1 here, so the only thing that's common in the 3 terms is 1, so that's a trivial thing. There's a b here, there's no b here, so I can't take anything out. Then you look at the number of terms. I have 3 terms, and then you check the degree. If it's 2, I can use the AC method. So I have 3 terms with degree 2, or if it looks like this, ax squared plus bx plus c. If it looks like that, then I can use the AC method. So let's do that. So the first thing I want to do is I want to break it down into this. Okay, whatever the a is goes up here, so I have 1, 1, and again, and then 1. Because 1 is a trivial number here, we don't need to write that. So let's just skip that. And then we just put a b there, b, that's it. And then what goes next here, m and n. So let's figure those numbers out. So what do I want? I want to do a puzzle. I want two numbers. When I multiply, I get 1 times negative 28 is negative 28. And when I add, I get the middle number, which is 12. Now, you can do this in your head by just playing with numbers in your head, which is eventually what you want to do. The nice thing about, before I go any further, I just want to point out, the nice thing about the AC method is if a is 1, then this becomes a 1, this becomes a 1, this becomes a 1, so you don't have to worry about this at all. And then nothing. So that's why AC method gets a lot easier if a is 1, and which is what is in our case. Now, you can play with some numbers in your head and figure them out. If you cannot figure them out in your head, you can do them on the side mathematically, so I'll show you how to do that. But let me first show you by trial and error how to do it in your head. You want two numbers. When you multiply, you get negative 28, and when you add, you get 12. So the numbers are 14, okay, and negative 2. Think about it. 14 times negative 2 is negative 28, and 14 minus 2 is 12. So you can see those numbers work perfectly. So my numbers over here would be plus 14 minus 2. So I wrote this as a product. There's my answer. And the nice thing is, if I were to distribute this here, multiply here, I should get this back. I'm not going to do that, but always please take a few minutes on the test and exam to do that. You can always check to see if you factored things correctly. But let me show you how I came up with 14 and 2, negative 2. So I want my product to be negative 28. So now you ask yourself, what two numbers do I multiply to get 28? It'll be 1n, 28, 2n, 14. 3 doesn't give you 28, but 4 does, 4n. 7. 5 times nothing gives you 28. 6 doesn't go into 28. But the next number is 7 and 4. But we already have those here. So once you get something to repeat, you can stop. You don't need to look for any more factors. Okay. Now, this number is negative. Okay. So ask yourself, when you the only way you're going to get a negative product is if one of the numbers that you're multiplying is negative. So since the answer is negative, that tells me what? The only way that's going to happen is if one of these is negative. So you have to decide which one is it going to be. Well, that depends upon the middle term, because eventually you want to add them to a positive number, right? That tells me that the larger one should be positive and the smaller one should be negative. Okay, that's because when I multiply I'm going to get a negative. That's good. But also when I add, I want to get a positive number. So I want the bigger numbers to be positive, because when you take a bigger positive number and add a smaller negative number, the result is positive, which is what I want. Now look at all of these pairs. Look at the one that gives you positive 12. It's negative 2 plus 14 that gives you positive 12. That's how I found those two numbers. Okay, now this works really nice, this method that I just showed you, but sometimes it gets tedious if this number gets big. What if it was 280 or it was something really big, and then you're going to have to find a lot of factors. So that's why it's better to try to play and do these things in your head. But let's go on and keep looking at some examples. So let's say if I have x squared minus 10x minus 24. Again, there's nothing in common, so you look at the number of terms. I have 3 terms, degree 2, so I want to use the AC method. So let's do that. Okay, so since the leading coefficient is 1, I just get x. I don't need to put that 1 in the bottom. I want two numbers. When I multiply, I get negative 24, and when I add, I get negative 10. Because 1 times negative 24 is negative 24, and so on. So let's do this. Again, I'm going to do this the long way first instead of by just figuring out in my head. I want the product to be negative 24. What two numbers do I multiply to get 24? 1 and 24. I get 2 and 12. 3 and 8. 4 and 6. 5 doesn't go into 24. The next one would be what? 6 and 4. So you can stop because I already have those now. The answer is negative. That tells me what? One of them has to be negative. One of these factors has to be negative. One has to be positive. To decide which one is negative and which one's positive, you look at the sum. The sum is negative, right? That tells me the larger ones have to be negative, and then the smaller ones will have to be positive, because when I add them I want to get a negative answer. So which one gives you negative 10? In this case the number is positive 2 and negative 12. So you get positive 2 and negative 12. There's your answer. Okay, so that's how we factor polynomials of degree 2 with 3 terms. Okay, so I gave you 2 examples, okay, where the leading coefficient was 1, and I'll do one final one before we move on. Okay, this one's going to be a little bit different, so you guys can see I have x squared plus 12xy plus y squared. This is still a 3-term polynomial. It doesn't look like this. It's just a variation of this. It's a special case. If I throw in a y here and throw in a y here, then y squared, then it looks exactly like that. Now, the reason why we put x at the beginning here, because when I multiply this out, what is x times x? I'll get the x squared that I'm looking for. Is that okay? Now if I had a y here, then clearly that tells me I'll have to throw in a y at the end, because when I multiply these two I should get y times y is what? Y squared. So the only difference between the two problems that I just did and this one, okay, and I should really put 36 here, sorry, is that I have 2 variables. It's still a degree 2 polynomial, you can clearly see that. So let's go ahead and use the AC method. The leading coefficient is 1, so that's nice. So we get an x and an x. And because we have a y squared at the end, I'll have to throw in a y and a y. That's important. Okay. Now, everything else is exactly the same as before. I need to find 2 numbers m and n. They go here. I just need to put them in there. Okay. So I want to find 2 numbers m and n. When I multiply, I get 1 times 36 is 36. And when I add, I get 12. Again, you can do this in your head. You can clearly see the number as 6 and 6. 6 plus 6 is 12, and 6 times 6 is 36. You already know the answer. So I would put in plus 6 here and plus 6 here. Okay. Oops, I'm not done yet. Because these are exactly the same, I can be a little bit more creative and write them in a more compact form as this. Okay. Now if you wanted to check your answer, this looks a lot like a binomial because you have two terms squared, a binomial squared. So if you remember, how did we do that? If you had a binomial squared like this, we wrote it as what? A squared plus 2ab plus b squared from the last section. I asked you to memorize this formula if you recall. So let's do that. In our case, what do we have here? I get a is your first term of the binomial, b is the second term. So I get a squared, so you get x squared, plus I get ab, so you multiply these two, so you get 6xy, and then you multiply that by 2, so you get 12xy, plus you get b squared. B is the second term of the binomial. In our case, it's 6y. 6y times 6y is what? 36y squared, which is what we had. So we know we factored this correctly. Okay, so keep that in mind when you're factoring. You can always go back and check your answers by multiplying it out like I just did here using this formula. If you didn't want to use the formula, you could have just distributed here, and you could have also multiplied it out that way to check it. But let me show you how I got 6 and 6. I have 36. What are the factors of 36? 1 and 36, 2 and 18, 3 and 12, 4 and 9, 5 doesn't go into 36, 6 and 6, 8 doesn't go into 36, but then I have 9 and 4, but I already have 4 and 9, so I can stop. Okay. Now this product is positive. Well, ask yourself, how do you get positive answers? If either both the numbers are positive or they're both negative, because two negatives make a positive, or if you have two positives, you still get a positive when you multiply. So I know they're either both going to be positive or they're both going to be negative. And to figure it out which one it is, you look at the sum. The sum is positive. That tells me what they're both going to be positive, because eventually I want to add these to get a positive number, so I can't have both negatives, which gives you a positive 12 that you're looking for. It's 6 and 6. So you can see that that's how we found those numbers. Let's take a look at another example. So far we looked at a whole bunch of examples where the leading coefficient was 1. So let's dive into problems where the leading coefficient is no longer 1. Okay, so we can see how we can come up with solutions to those problems, because those get a little bit more challenging. Okay, so we have, let's say we have 6x squared plus 25x plus 4. This is a degree 2 polynomial. There's nothing in common, so we don't have to worry about the greatest common factor. I have 3 terms, so I need to use the AC method. So let's do that. So the first thing I do, since I have a leading coefficient, I put 6x here. Go back and look at my notes. You can see we need to do that. We also need to put that 6, just the 6 on the bottom. Okay. Then we do a calculations to find m. I want m times n is going to be 6 times 4, which is 24. And m plus n is going to be 25. So I want two numbers. When I multiply, I get 24, and when I add, I get 25. You can do that number tree and figure them out. You can take 24 and go 124, 212, 38, 4, 6. The next is 5 doesn't go, so you get 6, 4, so you stop. Since the product is positive, that tells me either they're both positive or they're both negative. Which one is it? Look at the sum. The sum is positive. That tells me they're both positive. So which one gives me 25? 1 and 24. So you get plus 1 plus 24. And at this stage you might think you're done, but remember what I said. The key thing to the AC method is the number in the bottom should always cancel. Look at, I'm left with these two I found these two factors. What's common in this one? There's a 6 here and a 24 here. 6 divides both of them, doesn't it? So let's take that 6 out. So we get 6x plus 1. I'm going to take that 6 out. I get x plus 4. Divide that by 6. Since it's multiplication, I can cancel. So I'm left with 6x plus 1 times x plus 4. So there's your answer to that problem. Okay. So the AC method, when the leading coefficient is not a 1, takes a little work to do, but it really works out very nicely. The thing is to always remember the number in the bottom should cancel. I already gave you that. So you should be able to take something out from the top to be able to do that. Let's take a look at another example. Let's say if I have 8a squared minus 26a plus 15. Okay. Again, nothing in common, so I don't have to worry about the greatest common factor. I have 3 terms to agree to, so I'm going to use the AC method. Leading coefficient is not a 1, so I get 8a. We get 8a. And then throw in an 8 on the bottom. There we go. So let's do our calculations. I want two numbers. When I multiply, I get 8 times 15, okay, which is 120. And then when I add, I get negative 26. Okay. So, and you can clearly see this is going to take some work to do. Why is this going to take some work to do? Okay. The reason for that is because that product is really, really big. So we have to do some work. Okay. So you can take your numbers 120 and start factoring it. You can get 1 and 120, 2 and 60, 3 and 40, 4 and 30. We get 5 and 24. Then 6 doesn't go into it, 7 doesn't go into it. You get 8 and 15. 9 doesn't go into it, 10 and 12. And then the next one would be 12 and 10. So there's lots of factors here. The product is positive, so I know either they're all positive, or they're all negative. Since the sum is negative, that tells me they're all negative. I'm hoping that makes sense to you, because when we add these, we want a negative number, so they have to be negative, both of them. And when we multiply, we get a positive number. Which one gives you negative 26? It's going to be, let's see, negative, not that one. We have, did I miss one? Let's see. It's 20 and 6. Where's that? Oh, I missed a 6 here. Shoot. My bad. So it should be negative 6 and minus 20. That'll give you 26. And then there was 8 and 15. And then negative 10 and negative 12. So you can see when you get numbers get big, the factors get huge. So I get the one I'm looking for is this one. Negative 6 times negative 20 is positive 120. Negative 6 plus negative 20 is negative 26. So you get negative 6 minus 20. So remember, you're not done, because this 8 should cancel. What's common in this guy here? If you notice, there's 4 divides 8 and, 2 divides 8 and 2 divides 6. So let's take that 2 out. So I get 4a minus 3. What's common in this one? A 4, because 4 divides 8, so you get 2a, and 4 divides 20, so you get 5 divided by 8. What is 2 times 4? 8, so this will cancel this 8. So your answer is 4a minus 3 and 2a minus 5. So there's your answer to that problem. Okay, so when you're doing these problems, the key thing is to finding those numbers m and n. And if you can do them in your head, it's nice. It cuts down on all this tedious work, especially when the numbers get big. Okay, let me do one last example and then we'll move on. Okay, let's say if I have, I'll find something decent to do. Oh, okay. Let's say we have 2x squared plus 14xy minus 16y squared. Alright, so let's take a look at this one. So the first thing we do is greatest common factor. This time I do have something in common, because 2 divides this, 2 divides this, and 2 divides this. So we do need to do that. So let's take that 2 out. Whatever greatest common factor means, whatever number divides all of them, we want to take that out. So I'm left with x squared plus 7xy minus 8y squared. Okay. The next thing we want to do is what? We want to look at the number of terms. I have 3 terms. I want to use the AC method since it's degree 2. So let's do that. So let's put x here and a y, x and a y, and you know why we are doing that. This time the leading coefficient is 1 here, not a 2, the 1 here. I don't need to put 1 on the bottom, and I'm putting a y at the end here because of the y squared that I want. So what do I want? I want two numbers. When I multiply, I get 1 times negative 8 is negative 8, and when we add, we get positive 7. You can create that tree like I have been doing, or you can just do it in your head. The two numbers are what? Okay, they're going to be positive 8 and negative 1. So it's going to be positive 8 and negative 1. And those are your factors for that problem. We're done. You can see when the leading coefficient is 1, it goes a little bit easier than when it's not a 1. Okay, but the idea is still the same, so you just have to follow through on it and do it. Another example where the leading coefficient is, let's see if I can find, if we can set up another problem that we can do where we have to take something out before we factor them. Well, let's do this one. Let's say if I have I don't want to use big numbers. I'm trying to come up with some smaller numbers that you guys can do, so that way it's easier for you guys to factor, because with bigger numbers it's sometimes harder to factor. Okay, alright, well, bigger numbers are more fun to look at, but they get messy when we are trying to factor them. Okay, how about this one? We have we have 2x squared plus 5x plus 3. So nothing in common. There's a leading term, degree 2, so we want to use the AC method. We have 2x, 2x, and 3. I'm sorry, and 2. I want two numbers. When I multiply, I get 2 times 3 is 6, and when we add, we get the middle term, which is 5. What two numbers behave that way? Well, you can do it in your head, and you can see m and n would have to be 2 and 3. 2 times 3 is 6, and 2 plus 3 is 5. So it's plus 2 and plus 3. The 2 on the bottom should cancel. What's common in these two terms is a 2. So I can take that out. So I get x plus 1. I get 2x plus 3 divided by 2. The 2's cancelled since it's multiplication, and these are your factors. X plus 1 times 2x plus 3. And you can always multiply them out to see if they actually do work. So keep that in mind. You can always multiply those out to see if they actually work. You're not limited to just factoring, but you can always check your answers too. Alright, so that's all about factoring a 3-term problem. Let's take a look at the last topic in this section when we have 4-term polynomial. Okay, so factoring a 4-term polynomial, and the way we do that is by grouping. So this is by far the easiest way to factor, is by grouping. Okay, so let's go ahead and take a look at it. So let's say if I have this. By the way, before I go any further, I should mention, like in this very first example, or any of these examples for that matter, but I just want to use the first one because that's the easiest one to explain it. What if I change this to a plus? So now I want a plus here. So then all of these, so I want two numbers. When I multiply, I get 28. Okay, and when I add, I get positive 12. So I know they both would have to be positive, because the only way I get a positive product is if either they're both positive or both negative. In this case, the sum is positive. So I want to find which of these pairs add up to 12. I have 28 and 1 is 29. 2 plus 14 is 16. 4 plus 7 is 13. So 11. So none of those add up to 12. That means this polynomial cannot be factored. Okay, and I'll show you before the end of this lecture how you can check that. There's a very easy, simple way to check that, whether a polynomial can be factored before you venture into trying to factor it, especially if the numbers are big. Okay, so I will show you that before the end. I forgot to do that earlier, but I'll come back and do that. Let me finish this though. The 4-term polynomial is really easy. We want to do it by grouping, and the best way to show you that is by actually just going ahead and doing some problems for you, because it makes it a lot easier for me to just do a couple examples for you. So let's say if I have 3x cubed plus x squared plus 6x plus 2. You can convince yourself that there's nothing in common in all 4 terms. So there's no greatest common factor. The next thing is you look at the number of terms. I have 1, 2, 3, 4. So I need to group. So we group the first 2 terms and we group the last 2 terms. So basically what we do by grouping is we actually create 2 new problems out of it. So I'm just going to use a different color to show you. So imagine you have this problem. Ignore everything else in this problem. Just pay attention to the yellow box. How would you factor that? You would look for the greatest common factor. What's common in those 2 things? There's an x squared common, so I'm left with what? 3x plus 1. Okay. Now let's look at this box as a separate problem. Okay, what's common in those 2 terms? Is it 2 common? But remember, these 2 boxes have to be connected somehow. So since there's a plus here, I'm going to take a plus 2 out here because I need to connect them. And there's a 2 common, so I take that out, so I'm left with 3x plus 1. So I took out a x squared from the first 2 terms and 2 from the other 2 terms. Students have a tendency to write it this way. That makes no sense because that's saying I'm multiplying all of this. So make sure you put whatever sign is out here, that comes out, because that's part of that connection that connects those 2 things. So we started with 4 terms. Okay. Now we are down to 2 terms, 1 and 2. So we get 2 terms. That's progress. What's common in those 2 terms? You can clearly see both of these terms have 3x plus 1 and 3x plus 1. So let's factor that out. Let's take that out. 3x plus 1 comes out. What am I left with then? If I take this and divide by 3x plus 1, they will cancel. So I'm left with just x squared. If I take this and divide by 3x plus 1, they will cancel. So I'm left with plus 2. Okay, and there's your answer. Now keep in mind, I should try to break this down further, but I cannot for 2 reasons. 2 cannot be written as a square, and there's a plus in the middle. There's no formula for sum of 2 squares. There's only a formula for difference of 2 squares. So let's take a look at another example of a 4-term polynomial. So that's how we factor 4-term polynomials. They're fairly straightforward. It's just a matter of, going through the motions. Alright, so let's take a look at this one. Let's say if you have 2x cubed, x cubed minus x squared. Let's do 3x squared minus 4x plus 12. Okay. Again, you can convince yourself there's nothing in common in all 3 terms, so there's no greatest common factor. Then you want to look at the number of terms. I have 4 terms, so I need to group. Let's group first 2 and the last 2. What's common in the first 2 terms? Again, I have an x squared common, so I can take that out. What am I left with? I'm left with x minus 3. Now here comes the important part. In the last problem I told you, whenever we group, we have to connect those 2 pieces that we are creating, and we use whatever sign is in the middle to connect them. Out here, what sign is in the middle? Negative, so I'm going to put that negative there. Now what's common in these 2 terms? A 4. So I'm really taking out a negative 4. So keep that in mind. So if I take out a negative 4, what is negative 4 divided by negative 4? Just 1, so I just get an x. 12 divided by negative 4 is negative 3. So whatever I take out, you divide each term by that quantity, right? So in this case, I took out a negative 4 because the sign was here and I needed to take that sign out. Okay. Another way to think about it is, remember, I told you to imagine these are two separate problems. So if this is a separate problem, what did we talk about a while back? We always want the leading coefficient of the polynomial to be positive, so we want to take this negative out. So that's another reason why you know you have to take that negative out. Now what happened? We started with 4 terms, we're down to 2. What's common in these two terms? There's an x minus 3 here, there's an x minus 3 here. So let's take that out. So what am I left with? I have an x squared left because this x minus 3 got taken out, so I'm left with x squared. This got taken out, so I'm left with minus 4. So now I'm not done, because this I can break down further, and you can do that on the side. I have what? X squared minus 4, nothing in common. I have two terms, and so I want to use a formula, and 4 can be written as a square, so I know I want to do this. My a is x here, and b is 2, so I want to use difference of two squares, so you get the product of the conjugates. So you get x minus 2 and x plus 2. So we get x minus 3 on the outside here, then we get x minus 2 and x plus 2. So those are the factors of that problem. Okay. One last example of a 4-term polynomial. So let's take a look at this. We have let's say we have a cubed plus ba squared plus a plus b. Okay. Again, you can convince yourself there's nothing in common in all four terms. So you look at the number of terms. We have 4 terms, so we need to group. What's common in the first two terms? There's an a squared, so I'm left with a plus b. Whatever sign is here comes out. We talked about that. That's the connector for us. What's common in these two terms? There's nothing in common, but there's always 1. Like I said, 1 is a trivial thing that's common to everything. So in this case, you take out a 1, so we get a plus b. Because 1 times a is a, 1 times b is b, so you get that back. We started with 4 terms, down to 2 terms. What's common in these two terms? A plus b and a plus b. So let's take that out. You're left with a squared plus 1. Now you might be tempted to break this down further, because 1 can be written as a squared. I get a squared plus 1 squared. But the only problem is this is a sum. There's no formula for sum of two squares. So this is the best we can do here. Okay, and that's how you factor a 4-term polynomial. Now, before I go any further, let me go back and talk about when can a polynomial of the form ax squared plus bx plus c be factored. So this is something I should have mentioned before I did the 4-term polynomials, but let's go ahead and do it at this stage. How do we know this can be factored? Because I showed you a while back that not every polynomial can be factored, because you cannot just find those numbers like when we did over here with 28, I think so. With this one, if I had made this positive, this no longer can be factored anymore. So how do we know a polynomial can be factored? What is the magic calculation that we need to perform so that the polynomial can be factored? So let's take a look at how we go about doing that. Okay, so let's say that a polynomial of this form of degree 2 with 3 terms can be factored if the discriminant, I'll explain what that is. The discriminant d, which is equal to b squared minus 4ac, where b is from here, a, c's are from here. The discriminant d is a perfect square. So if this discriminant is a perfect square, then the polynomial can be factored. And when I say the polynomial, I'm talking about the degree 2 polynomial of this type. Okay, so this is a very simple calculation you can perform to do this. So let's check it. Okay, so let's say if I gave you something like this. If I give you 6x squared minus x minus 12. Now 6 times negative 12 is negative 72, and that's fairly big number, not a very big, but you can try to figure out the factors for this and try to use the AC method to do this. There's nothing in common, so we do want to do the AC method. But before I do that, let's actually check to see if it can be factored. If it can, we'll factor it. So first thing I need to do is calculate the discriminant. D is equal to b squared minus 4ac. What is a? In this case, a is 6. B is the number here, negative 1. Let's put parentheses. And c is negative 12. So let's put parentheses. Remember to put parentheses when you plug in things into a formula. So you get b squared. So you get negative 1 squared minus 4 times a times c. So we get minus 1 squared is 1. Negative 4 times 6 is negative 24. Okay, and negative 24 times 12 is positive 288. So we end up with 289. Now 289 is a perfect square, because if I take 17 and multiply it by 17, I get 289. That means 17 squared is 289. So 289 is a perfect square. That tells me what? That this polynomial can be factored. So let's go ahead and do it. So I use the AC method. I have 6x divided by 6. I want two numbers. When I multiply, I get negative 72, and when I add, I get negative 1. 6 times negative 12 is negative 72. When you add, you get negative 1. And you can do the tree again, or you can just guess, figure it out in your head. Not guess, but figure it out in your head. They're negative 9 and positive 8. Negative 9 and 8. Negative 9 times 8 is negative 72. Negative 9 plus 8 is negative 1. So I get negative 9 and positive 8. Now what's common in this first factor here? There's a 3 common, so I get 2x minus 3. And what's common here are 2. So I get 3x plus 4 divided by 6. Because that 6 should always cancel, right? That's why I'm taking something out. What is 3 times 2 here? It's 6, so I can cancel that. So my answer is 2x minus 3 and 3x plus 4. So you can easily check to see if something can be factored by calculating the discriminant. Let me do one example where it cannot be factored, so you guys can see that. So let's say if I have x squared plus 5x minus 36. Okay, so let's try to find the discriminant. A is 1, B is 5, and C is negative 36. Okay. Actually, this, you can't factor this. Well, let's do it. Since it can be factored, might as well show you that it can be. 4ac. So I get 5 squared minus 4 times 1 times negative 36. Those parentheses come handy. So you get 25. Negative 4 times 1 is negative 4. Negative 4 times negative is a positive something. So 4 times 36 is 120 plus 24 is 144, which gives you 169, which is 13 squared. So it's a perfect square. So it can be factored. You can easily do it. You get x. We get x. I want two numbers. When I multiply, I get negative 36, and when I add, I get 5. The numbers are negative 9 and positive 9 and negative 4. You can convince yourself of that. Well, let me give you an example where it cannot be factored, since I gave you a whole bunch that can be. How about this? X squared plus 2x plus 15. Okay. Let's do this. Let's make it minus and make this a 3. Alright, so let's do that. My A is 1, B is 3, and C is negative 15. Okay, So I get d is equal to b squared minus 4ac. So I get 3 squared minus 4 times 1 times negative 15. So I get 9 plus 60. I get 69. 69 is not a perfect square. There's no number whose square is 69, so this cannot be factored. Okay, let me show you just a little variation of this problem. Let's say if I had this. Okay, so what would have happened now? Let's A is 1, B is 2, and C is 15. So I get D is equal to B squared minus 4AC. So I get 2 squared minus 4 times 1 times 15. So I get 4 minus 60, right? So that gives me 56 negative. Now remember, we're trying to find out if this is a perfect square, but that makes no sense, because if I square any number, if I take 2 times 2 or negative 2 times negative 2, whatever, I always get a positive number. So will I ever get negative number back? No. So that tells me that this cannot be factored. So this section was long because it's a very important section, like I said at the beginning of this section. So please make sure you guys do your homework and master the idea of factoring and get very, very fluid with it. As soon as you see a problem and they ask you to factor, you should be able to just jump right into it and do it without even thinking about it. Okay?